Think about why you can swim through water, why clouds drift across the sky, or why lava moves down a volcano's slope. Well, what all these have in common is that they're made of substances that flow. We call them fluids. And this single idea makes them unique. So, unlike solids, which keep their shape, fluids adapt. They take the shape of whatever container they are in. So, before we get into any formulas and equations, let's revisit two simple but fundamental ideas. These are density and pressure. So, density, let's picture it, tells us how much mass is packed into a given volume of a substance. Mathematically, we write this as rho is equal to m upon v. So, for example, if you have 4 kilograms of a fluid in a container with a volume of 2 meter cube, the density is 4 divided by 2, which is 2 kilogram per meter cube. You could say the properties of this substance allow 2 kilogram of it to be packed in a meter cube of space. Simple enough. Note that both mass and volume have magnitude only, no direction. So, density inherits that property and is a scalar. Now, here's an interesting point. Gases, which are also fluids, show a strong variation of density with pressure. Compress a gas and you noticeably increase its density because you're packing the same mass in a smaller space or volume. Liquids, on the other hand, are essentially incompressible. Their density stays nearly constant even if you crank up the pressure. Now, let's talk about the idea of pressure. So, picture this. Here is a container of fluid and let us say we insert a pressure sensing device into it. And this sensor is nothing fancy. In concept, it's basically a piston with a surface area A attached to a spring, and when the fluid pushes on it, the piston compresses the spring, and the amount of compression tells us the pressure the fluid is exerting. And in simple mathematical terms, we can express that as P is equal to F upon A. And here, F is simply the magnitude of the normal force acting on the surface area A, and this force gets spread out evenly over the entire area when we deal with fluids. Now, here's something that often confuses students, that is, pressure is a scalar quantity. It has magnitude but no direction. And you might rightly wonder how that can be when we calculate it using force, which is a vector. And the answer to it is that we use only the magnitude of the force acting normal to the surface and we ignore its direction. That's why pressure expressed as P is equal to F upon A is purely a scalar. Another way we can identify pressure to be a scalar, and I find this a lot more convincing, is that in fluids, the force exerted on any surface by the fluid is always perpendicular to that surface, regardless of orientation. So, as an example, if you are standing in water, the force acting on your body due to water would always be perpendicular to the contours of your body. And since it is always perpendicular, it means it can have no other direction, and therefore it is meaningless to say that it can be a vector. Now, when we talk about atmospheric pressure, the very name tells us that it is nothing but the combined weight of, you could say, all the layers of air stacked above us that are pressing down and creating the pressure. That, as a standard practice, we measure at sea level. So, at high altitudes, atmospheric pressure is lower because there are fewer layers of air above you. In fact, at the summit of Mount Everest, that is little less than 9,000 meters, atmospheric pressure is roughly 33 kilopascal, or about 1/3 of the sea level pressure. Alright, so here is a container filled with water. or for that matter, any liquid, and it is open to the atmosphere. Now, you've probably noticed that as you dive deeper underwater, you feel more pressure on your body. And why does that happen? Well, pressure changes from the surface of the water down to the depths below it. And for convenience, let's define the surface here as y is equal to 0. That is, this becomes the origin. We'll take the positive y direction as upward and the negative y as downward into the liquid. Now, what we do is imagine a cylinder of water with a horizontal base of area A such that y1 and y2 are the depths of the upper and the lower faces. And you can see both are negative numbers. Then, if we were to draw a free body diagram of the cylinder, we can see three forces acting on it. And they are F1 that acts on the upper face, force F2 that acts on the bottom surface, and finally we have force mg, or the weight of this water cylinder in downward direction, and here m is the mass of the water in the cylinder. Now, since this cylinder is static, that is, it is not moving, it is stationary, the forces should balance out. That is, the net force should equal 0. So we can write F2 is equal to F1 plus mg. Now, expressing this equation in terms of pressure, we write F1 is equal to P1A and F2 is equal to P2A. Also, mass m of water in the cylinder can be expressed as rho v, where the cylinder's volume v can be written as the face area A and height h that we can see is y1 minus y2. So mg is equal to rho ga times y1 minus y2. And this equation then becomes P2A is equal to P1A plus rho ga times y1 minus y2. And notice that A gets eliminated from this equation, which means that you could have a small face cylinder or large. It would not change the end result that we are trying to derive, and that is P2, or the pressure here, is equal to P1 plus rho g into y1 minus y2. So the physical interpretation of this equation is that the pressure at the deeper face P2 equals the pressure at the upper face P1 plus the extra pressure produced by the weight of the fluid column between the two faces. Again, it doesn't matter whether the cross section is large or small. Pressure depends only on depth, not on the size or shape of the imaginary cylinder. So, let us say now we wish to find the pressure P at depth h below the liquid surface. Then using this equation, y1 becomes this level here, that is 0, and y2 becomes this, or a distance h below the surface. And P1 is the atmospheric pressure, often labeled as P0. And if we substitute these values, we get P is equal to P0 plus rho g into 0 minus h, or P is equal to P0 plus rho g h. Again, you should try to interpret this equation physically, and what you see is the pressure at this point, or rather level, is the sum of pressure due to this section of fluid plus the atmospheric pressure that adds on. And this total pressure is often termed as absolute pressure. So another interesting thing that you would have noticed by now is that the pressure at any depth in the liquid depends on that depth and has no relation to any horizontal dimension, and therefore this equation holds irrespective of the shape of the container. So the pressure at these two levels in both containers will be the same, simply because the depth below the surface in either case is the same. Now, if the atmospheric pressure is not considered in this equation, then this quantity is called the gauge pressure. So you can say that if you subtract the atmospheric pressure from the absolute pressure, you get the gauge pressure. And you see, it makes more sense to use gauge pressure since atmospheric pressure acts everywhere in the fluid and on all surfaces equally. That is, it gets added to the pressure at every depth. Therefore, when we compare the pressure at two different depths, the atmospheric pressure cancels out, leaving only the difference in pressure due to the weight of the fluid between those levels. And this is why in many problems, what really matters is the difference in pressure between 2 points. The absolute pressure value only matters if we care about the total force including atmospheric pressure. Now, this equation can be used to establish pressure at any point above the liquid surface as well. As an example, if you want to know the atmospheric pressure at a distance d above this level, all we do is take y1 is equal to 0, p1 is equal to p0, and y2 is equal to d. And for density, we take rho is equal to rho air, since the fluid here is the air. And of course, we assume that the density of the air remains the same. So we get P is equal to P0 plus rho air into G into 0 minus D, which gives us P is equal to P0 minus rho air into G into D. And don't forget to notice that this pressure P is less than P0 because of this quantity getting subtracted from P0. And this should make sense to you simply because moving from here to here, we have fewer layers of fluid, that is air here, above the point. And that results in reduced pressure. Alright, let's now work through a practical example, something that will lock in your understanding of this concept. So what we have here is a U-tube with two liquids in static equilibrium. So we have water of density rho W equal to 998 kilogram per meter cube and oil with density rho naught, that is unknown. Also, we can see that L is equal to 135 millimeter and D is equal to 12.3 millimeter. And the question is, what is the density of the oil? So there are two things that you should observe. The pressure at this level, let us call it Pi, depends on the density of the oil and this height. And two, the water pressure at this level should be the same as Pi, simply because in static equilibrium, pressure at same level in a continuous fluid should be the same. And you should imagine that if it were not the same, what would happen? The liquid would not remain static but move. So for this side, we can write the equation as Pi is equal to P0 plus rho W times GL. And this side, you see the interface is a distance L plus D below the free surface of the oil. So we get Pi is equal to P0 plus rho naught into G into L plus D. Now we can equate these two equations, and what we get is rho naught is equal to rho W into L upon L plus D. And if you plug in the values, you get the density of the oil equals 915 kilogram per meter cube. And you must observe that the answer does not depend on the atmospheric pressure P0 or the free fall acceleration G. So the next time when you open a soda bottle, I don't want you to think about the fizz and the flavor. Ask yourself, how is the pressure changing right now? Because once you start seeing these patterns, you'll begin predicting the physics of everyday life without even thinking about it. And that's where real mastery begins.